Does anybody have any questions before we begin? Okay. Well, we're looking at section 4.4. So, talking about symmetry. The author begins the section with a question: what is the most symmetric shape that you can think of? So, what is the most symmetric shape that you can think of? Anybody think of any symmetric shapes, even if it's not the most symmetric shape?
Square.
A square? Okay, so let's look at a square. So what makes a square symmetrical?
If you draw a line in the middle, it's the same on both sides.
So if you draw a line down the middle, it's the same on both sides. Yep, sure enough. And then you can do it different ways too, different middles. So that is a very symmetrical shape. Look at all the ways I can draw lines across it, and one half is the same as the other half. Are there any other symmetrical shapes that you can think of? Yes? A circle. Okay, a circle is also symmetrical. And what makes a circle symmetrical? Is it the same reason? Like you can draw lines through it and one half looks like the other half? Those are indeed symmetrical shapes. Well, people are drawn to symmetry. Have any of you ever seen studies about symmetrical faces? So this is a picture in your textbook. An average computer-generated face made from 32 actual faces. And it's very symmetrical. One half of the face looks like the other. And people tend to find symmetry attractive. So your author says a little bit, we might think the most beautiful faces would be extreme in some way, thin or chiseled, but the faces most often chosen as beautiful are extremely, well, average and symmetrical. So we're attracted to symmetry, and here you see symmetry in tiling the plane. So that's actually what we're going to look at, symmetry in tiling the plane. So you can think of it as a floor. When you tile a floor, what kinds of floor tilings can you cover the floor with? So we're looking for one tile that you could cover the whole floor with. For example, the square, right? You have a square as the first item here, and if you look at your floor that you're sitting by, it's covered in squares. So you could tile the floor with squares, and it would look like graph paper. What other shapes can you tile the floor with? Anybody looked at any bathroom floors lately, or
Triangles.
triangles? Let's see, tile with triangles. Yeah, that would work. Okay, squares or triangles. Anybody see any other floor tilings?
Rectangles.
Rectangles, sure. So squares, triangles, rectangles. Any other shapes? Octagons. Oops. I started to draw a hexagon. Oh, you know what? I think if you use an octagon, you have to incorporate squares. But I have seen hexagons. So I think hexagons you don't have to incorporate a square with. Well, we're talking about symmetry. So what is symmetry anyway? Anybody have any ideas? What's the same on both sides? Yep. Okay, so that's one way to discuss it. We feel like the same on the both sides. We're going to look specifically now at symmetry in a plane. So we're going to look at rigid symmetry in a plane. So if we're looking at just one shape, then we would think, okay, it's symmetric if one half is the same as the other half. But now we're going to look at a whole plane, and so I have some of these tilings that we've talked about, and one more that you'll see. They're in these little groups. So some of these groups have this oh, the screen froze. Okay, that didn't help. It's like it lost the document camera. Yep. Lost it. It just turned itself off. Okay, that's okay. I'll hand these out while it's doing that. So some of these have crimped corners, and then every other one, instead of having crimped corners, is two little half sheets of paper. So I thought that way I could sort of, because I couldn't get the photocopier to print in two spots. So like you can have these two that are loose, and then pass this one with the crimped corners down. Okay. Here's a set of loose ones. And these are crimped, and then I'll give you a loose set to pass down. What is that? I think you have a loose set. No, one more paper first. So, one set and two sets. Okay. Okay, so four. So I should be able to give two loose sets and two crimped sets. And 4, 5, 6, 7. So loose set, crimped set. 1, 2, 3, 4, 5. Okay, we'll just start passing them down and see, okay? So you either get a crimp set or there's two loose pieces of paper that go together. So yeah, yours is stuck together. Oh, there are two loose pieces of paper, two loose half sheets, or yeah, your crimped ones are crimped together. So I cut these in half, right? And the photocopier would only crimp one corner. And so half of these have crimped and half don't. That was my idea of how I would save time. It didn't quite work because then I had to sort them all anyway. Okay, so you have two little half sheets is what you should end up with. Either stuck together or loose. And you got yours, two little half sheets, either stuck together or loose. And there's the extra. Does everybody have two little half sheets? Gonna hand out that many extra. So you had mentioned these different ways of tiling, and so imagine this goes on forever, and we're tiling the plane here with the triangles, or with this one we haven't looked at. This is triangles, but we'll look at that later. That doesn't look symmetrical, does it? It's like crazy. Okay, and here's the hexagons we talked about, and squares, which is disguised as graph paper. Okay. So what I have then is some transparencies to help think about how symmetry in a plane is going to be described. So I have some transparencies for you to use. There's enough for everybody to grab two different kinds. So I have all three kinds. And then you can work with someone to try the different kinds, the other kinds that you don't have. Okay, so could pull it apart, please. That's good. So everybody take two, and you won't get all three different kinds, but then you can work with some together. I think these will be less sticky after you get in the back end. So don't draw out the clear ones, please. I'm going to use those again. So 3. Is that 2? These two should be like that. Now I'm just setting this all down here and everybody make two. One of 2 different kinds. I would have just had everybody have one if everybody came to class. Hopefully students online are watching this if you missed class. I don't have a good way for you to print these out unless you at home have transparency. So take one of the ones that you have, whichever one, like here I'll grab the one that's square, and work with the square printout and see if you can describe symmetry in a plane, in tiling a plane, by comparing the clear transparency with the paper. So in other words, how many different ways can you move that transparency and have it land on top of the original tiling? How many different ways can you transform the transparency and still end up lying on the tile? Okay, so flipping, turning, how many degrees do you have to turn? If you turn it, what if you just slide it? Do you have to slide it up? Do you have to slide it down? So whichever one you have, try that. Good thing I saved some, or I would have sent them all out and not been able to try it myself. Okay, so like these are not lined up, but I could line them up. And once they're lined up, how can I move the transparency so I'm still staying lined up? If you get done with yours and you want to see if someone behind you has a different one to use, that would be great. So we'll start with the hexagon just because I think it's so fun to slide it off. Isn't it fun when you slide it off and it makes these cool shapes? Okay. All right, but that's not what we're looking for. We're looking for matching. So which ways could you, what different things could you do with the transparency and still have the transparency line up with the paper copy?
Go straight up and down.
Straight up and down? Okay, straight up and down. Let me try that once. Okay, so straight up and down, but not that much. You gotta go that much. Okay, so straight up and down. So vertical shift. What other directions could you move the transparency or ways? Did anybody try left and right? Did that work? I didn't try left and right. Let's try left and right. Okay, so left and right works. Did anybody try flipping it over upside down? Let's try that. Okay, so you can flip it upside down and still get it to line up as well. Did anybody try turning it or rotating? Well, that didn't work. You got to rotate a little more, maybe? Is it going to work at all? Eventually. Okay, so that looks like you have to rotate a certain number of degrees, like more than square, so maybe 120 degrees, which kind of makes sense when you have, I think these have 120 degree angles right here on the corners. Okay, so this has a rotational symmetry in the plane, and then you can also shift it up or down or left or right, or you can flip it. Okay, so this one has lots of different symmetry going on. How about the triangle one? Someone tell me one of the symmetries you found with that one. Left and right? Okay, so left and right. So I'll just shift this over. Oh yeah, there we go. It's probably a better fit if it's not manually made. I just took triangles on a Word document and fit them together. So there's a little bit of error just because I did not do that perfectly. Okay, so left and right. What other symmetries did this have in the plane? Did anybody try a vertical shift? Did that work? Anybody? I didn't try it. Okay. Vertical shift, let's try that. Okay, so yeah, a vertical shift would work. Did anybody flip it over? You can just nod. Did anybody flip it over? Yeah, and did that work? Yes, okay. All right, so yeah, that works. And then did anybody try turning it in a rotation? Let's try that and see if that works. Okay, that looks like you turned it about the same amount as the other one, 120 degrees. I wonder if we could have turned it 60 degrees, since each of those angles is 60 degrees. Okay, so yeah, that has the same three types of symmetry in the plane: the shifting, rotating, flipping, or I think I said one twice. Okay, let's try the squares. Where's my graph paper? It's on the back of one of these. So these squares, they're the easiest, aren't they? I mean, you just slide up or down, left or right, flip them. Or you can turn them also. You turn them, how much? 90 degrees, right? And then they line up. Well, let's go ahead and write down a definition then for symmetry, okay? So this is what we've been exploring with these overheads is called rigid symmetry in the plane. So rigid symmetry in a plane is a motion of the plane rigid symmetry of the plane is a motion of the plane that preserves the pattern. that preserves a pattern and does not shrink, stretch, or otherwise distort the plane. Well, that's a kind of symmetry we're most familiar with, I think, because of floor tilings. But there's another type of symmetry that's built on building tiles from tiles. Okay, so take your squares, for example. I keep wanting to grab a fresh one. I better put them over here and not waste them. I have plenty. Okay, so scalable symmetry is when you build the same shape on a larger scale using the tiles that you have. Okay, so for example, here I could see that I have a square that's being repeated, but I could also make a larger square. So I could think of this as 4 little squares and call it a super tile, and think of the pattern as the 4 super tiles being repeated over and over instead of the 1 single tile being repeated over and over. So this is scalable because if I take the original tile and make a big tile out of it and use that to build with, well, I get the same pattern. So if I take these 4 tiles and then build into another 4, exactly how I built this one. So I started with 1 and then I surrounded it with 3 more. So if I start with 1 and surround with 3 more 4x4s, of course I'm getting the same shape. So we start with something simple like squares and take a look at that. In some of your homework, your author asked about super tiles. So this 4x4 we would call a super tile. What would be the next tile size up that would still be a square? What's the smallest number of tiles you can use that is bigger than 4 tiles and still get a square?
6.
Let's see. Try 6. So where would I put the other 2? Right, left, up, or down?
Up and down.
Up and down. Okay, one here. Okay, so maybe that's not what you meant.
No.
Okay, so that's not quite square. So either I did something wrong or we need more tiles.
2 more.
2 more? Okay, where should I put 2 more?
At the bottom.
The bottom. Okay. So that's not a square either. So I'm looking to get a square, and I'm looking for the smallest number of tiles I can use and get a square. So I tried 6 and I tried 8. Anybody have other ideas we could try? Okay, well, you explore that. See if you can make a square out of the little squares and see how many tiles you need to do that. I made one with 16 and I made one with 4. Okay, so we had one with 4 and one with 16. Is there any in between that make a square? If you have it, raise your hand. Is it 9? Okay. Okay, so we find that 9 squares still make a square. So I'd made a super tile out of 4 squares, because it still made a square, and I could build with it yet and get the same shape. But we could put 9 squares together, and we could call that a super tile, because it's the next size up. Next size up. And I could take these squares then and continue to build. So this is symmetry of scale, because we're working with scales. We're looking at a small square, a medium square, a big square, and all of these, the small square, the medium super tile, and the larger super tile can all be put together to tile the plane, and you'll get the exact same figure. Let's write down what rigid symmetry is then. So or symmetry of scale, rather. So symmetry of scale, a pattern in the plane has symmetry of scale pattern in the plane has symmetry of scale or is scalable if the tiles that make up the pattern can be grouped into super tiles that still cover the plane and if scaled down can be rigidly moved to coincide with the original pattern. So symmetry of scale. A pattern in the plane has symmetry of scale or is scalable if the tiles that make up the pattern can be grouped into super tiles that still cover the plane, and if scaled down can be rigidly moved to coincide with the original pattern. So on your other 2 handouts, can you please, well, you have 3 more, but we're going to hold off on that. That one's crazy, right? We're going to hold off on that one. But on these other 2 patterns, this one and this one, can you look and see if they have symmetry of scale? I'm sorry, I covered up your. Is anybody still writing that now? Sorry. So look to see if they, other 2, the triangles and hexagons, have symmetry of scale. Look for super tiles that have the same shape as the original tile. And you can go ahead and outline a super tile, okay? And see if you can find multiple super tiles or super tiles. Okay, while you do that, I'm going to look up someone who's famous for tiling the plane in unique ways. I can't remember what I clicked. I think this one. Okay, so in the triangles, how many triangles were you able to put together to make a super tile? What's the least that you could use? 4, yeah. So just pick one and surround it with 3 more. Okay, good. Okay, so then that creates one that I'll outline in red. So super tile. And then what was the next size up? How many more did you have to add to that to still have an equilateral triangle? Oh, how many? 12? So you, did anybody find one with less?
Oh, 5.
I don't know if I can get a triangle with 5. Here.
No, I mean 5 more.
Oh, 5 more? Okay, yeah. Okay, so you added another row?
Yeah.
Yeah, that does give you 5 more. Okay. So there's a super tile. So if you find a way to make a super tile that you can form by, adding more copies to make the exact same shape, you found a way to pattern the plane, because then you can keep repeating that, right? You can keep, like with this 3, with these 4, if you decide you're going to make 4 triangles into a super tile, well, then you can take those 4 and make a really big tile that covers the plane. So it's bigger than the 9, but you found a way to cover the plane, so you're like building. So now I take these 4 bigger tiles and I can put them together in the exact same way. So finding a super tile is helpful to cover the plane. You can just build the same way you built the first tile and make a bigger tile. So this one had rigid symmetry, and it had scalable symmetry, or symmetry of scale. Because we could find a way to make super tiles that were larger copies of the original tile that covered the plane just like the original tile did. So we had rigid symmetry when we were moving the transparency around, and then we had symmetry of scale when we built the super tiles. Okay, how about on this one? Anybody find a way to make a hexagon out of hexagons? No, it's impossible, right? There is no scalability here. No symmetry of scale here. No matter how you try putting the hexagons together, you don't get another hexagon. You get interesting shapes, but not another hexagon. So no symmetry of scale. But we did have rigid symmetry. So you will need to be able to tell the two apart. Okay, rigid symmetry was where we could slide the transparency around on top and still land up on it, or we could rotate it So there's a number of different kinds of rigid symmetry, and this actually had all three kinds. It had flipping, rotating, and shifting up or down, or left or right. Okay, so no symmetry of scale on the hexagons, but it did have rigid symmetry. And last of all was really, first of all, the graph paper, the squares. This had rigid symmetry, where you move around the transparency, and it had symmetry of scale. Well, these are kind of boring shapes, aren't they? They're just like, oh, it's pretty simple. Okay, let's take a look at some beautiful symmetry created by Escher. So Escher was a graphic artist. He started out to be an architect and then switched over to a graphic art. And he made beautiful tilings of the plane. I wonder if I can make these larger. There we go. Beautiful tilings of the plane. So let's just take a look at this horse one, for example. You see he's tiled the plane all with horses. If we're just going to focus on that, I guess I'll click on it. What kind of symmetry does this tiling represent? Rigid? Well, we could go one at a time. Does it have rigid symmetry? Could you slide a transparency of this around and still have it land on itself?
Yeah.
Yeah, it does. It has rigid symmetry. Okay. How about symmetry of scale? Could you stick some of the horses together and make another horse? Yeah, no symmetry of scale here. Let's see if we see some of the other ones. So Escher makes beautiful works. Have any of you seen any of these before? Anybody? Some of them? Yeah, I think they make it into calendars and such. I thought this was interesting because it's so unusual. So they look like little children. Are they all the same child shape?
Yeah.
Okay, so they're all the same child shape. Now, does this have rigid symmetry?
Yes.
Yeah. So you could slide it. You could slide it diagonally too. You could make those yellows land up on top of themselves. It's nice that these are colored so you could see that. So it has rigid symmetry. Could you rotate it? I think if you rotated it, would you have to slide it also? Yeah, rotate and slide. Could you flip it? Would you have symmetry if you flip it? So that's a type of rigid symmetry too. Remember, we just flipped the clear transparency over. Would that work here? Maybe if you slid it too? I don't think that would work. Do you? I'm not thinking that would work. Okay, so we have several types of rigid symmetry. What about symmetry of scale? Could we put enough of these little children together to make another one, another child? Yeah, I don't think that's possible. Okay. So he doesn't always use the same shapes. Here we have a collection of two different shapes for tiling. But you could still have some symmetry going on. Okay, so pretend this extended to the whole plane. Does it have rigid symmetry? Could we slide a transparency over and or rotate it or flip it and get the same shape? Would it land on itself? I think you could slide left or right or up or down, right? Left or right or up or down, and the birds would land on themselves and the fish on themselves. Does this have the ability to be flipped? Could you flip it and have symmetry that way?
Yeah.
maybe.
Yeah, so flip it vertically. Yeah, flip it vertically and maybe slide it up as well a bit. So, for example, if we flip it, this bird would land over on where this one is, so you'd have to slide it up so it's facing in the direction over here. Okay, so several types of symmetry there, but not scalable. It's not scalable, is it? You can't build copies of the bird and fish together to make a bigger copy of a bird or fish. So Escher's work has lots of different rigid symmetries, but no scalable symmetries. I brought a symmetry example. I bring it every day to class, actually. This is my pencil case. I use it for my microphone. I have to have something big and bright to hold my microphone, or else I leave it in class, and then I'm in the next class going, how am I going to record this? There's no microphone. So this is my reminder bag. But I brought an overhead to see if it has rigid symmetry or symmetry of scale. So I have a clear overhead here. So write down at your desk what types of symmetry you think this has before we experiment, please. Okay, write down if it has rigid symmetry, and if it does, how. Are you going to slide up or down, left or right, flip, rotate, several of those? And then see if it has symmetry of scale. Can you build a super tile that looks like, I don't know how you would even think of it. Yeah, no, let's just say no. You just can't, right? You can't. If you think of this all as a unit and you're trying to build another one of these from it, you'd have to be trying to build those together. I'm pretty sure you can. Okay, let's test your ideas for symmetry, rigid symmetry though. Okay, so here's my overhead. I'll slide it diagonally. No, I'll just slide it left or right. Okay, so there I slid it left or right. So if you said left or right, that was perfect. It looks like we can slide it diagonally also. So if you said slide it diagonally. If we went far enough, we could slide it up and down. So we could slide it up and down too. So there's lots of shifting symmetry, or yeah, we'll call it shifting. So if you have that down, good. Did anybody put down rotational? Okay, so we have rotational symmetry as well. Okay, so you rotate and the shape lands on itself. So you have rotational symmetry, and we also have flipping symmetry going on. Okay. Well, I'd like to look at this super tile for a bit. Does anybody have any questions about symmetry before we do that? You know what? I think I'll hold off. The other class almost always has questions and takes longer than you. So we'll look at super tile, this other shape, next class. So please bring that. And also, please bring your platonic solids. So we'll get to...
Dropbox for symmetry.
For symmetry, we're going to put some work we do with this on Friday.
Okay.
So the Dropbox for 4.4 will be Friday. Thank you for reminding me.
Can I see the definition for symmetry stuff?
Yep. And here's the definitions again. And please bring your platonic solids Friday. We'll work on those Friday and probably Monday as well. I need the clear ones, please, for the next class. But you can keep the paper ones. So if you wouldn't mind putting the clear ones at the ends of the desk, it will make it easier for me to collect.